Hello everyone, today I'm going to talk about this poster, which is effect of scan path modifications on defect control and mechanical performance in LPBF tungsten. I'm the graduate lead. I'm really happy to work with these highly motivated undergrad students, and I'm grateful to my professors and the organizers of this wonderful event. My topic will be on tungsten, which is a critical refractory metal but very popular in aerospace and nuclear application. But the issue with tungsten is with laser powder bed fusion. Why? Because tungsten has very high ductile to brittle transition temperature mentioned here. But laser powder bed fusion is extremely rapid heating and cooling phenomena. This yields pores, cracks, defects to the tungsten sample, which makes it really difficult to make a successful part. So there has been lots of studies ongoing, like scan path modifications, border studies, or other expensive post-processing. But we don't want to focus on that. We want to focus on in situ technique, which can be used during the fabrication to improve the properties of the part itself. So we want to propose a triple exposure scan strategy, or TESS, as a directional preheating pass. What we expect is it will create a thermal pathway that will heal the cracks and pores as the sample is building up. Let me stretch a bit. What do I mean by this triple exposure scan strategy? So this is basically a simple additional scan, which is directional scan, as mentioned by this orange directional line. So it will be consistent in all the layers, which will be immediately followed by double exposed typical major pass, which is more common in laser powder bed fusion. So this will rotate by 67 degree each layer, but this will not rotate. It will be from 45 degree to 90 degree as the sample goes on. That's why I named them pH 1, pH 2, pH 3, and pH 4. Now I want to expand onto the result, because we categorize our sample in three outcomes, which are density measurement by Archimedes principle, the other one is mechanical testing, and the other one is the ACM characterization. So on the densification, our results indicate a significant improvement on densification across all test configuration. And we can see pH2 has the highest density noted here, which is 97.5%, and 1.6% increase in density. Then I want to talk about the ACM images. ACM images reveals a clear sensitivity to scan orientation. In pH2, as we can see, we see a healed microstructure, what we expected, while crack continuity was successfully arrested. That's why I see very smooth surface here. Conversely, pH3 shows those reappeared crack tracks, but in pH4, what we can see, the same kind of continuous cracks with additional defects on it. So we can expect that these are very directional dependent results. Now finally, I want to move on to the mechanical strength. Despite its lower density, pH1 showed the superior mechanical performance, and it showed an UTS value of 350 megapascal, which is a 10% improvement based on the reference. This presents a critical strength paradox. A peak mechanical performance did not correlate with maximum physical densification, and this is consistent with the current research that has been going on with tungsten. What has been shown that a best density sample can show worst performance in strength, which is consistent here. So finally we found that pH2 is the most effective for maybe physical crack mitigation, we can say, and pH1 optimizes the mechanical performance through tailored grain orientation. This is our expectation. What we suggest that our method can work as a specific application based. If the application is for densified parts, yes, the pH2 processing parameter will help. If it requires strength application, then pH1 might help. But if there is a middle ground required, then further investigation is required by EBSD and TEM. Thank you so much.